Whatever you want, you can open. It may be changed. No problem, right? Between them, only 5 minutes. Yeah. Yes. The first one is here.
So, my name is Anna Vorobyova, and I want to introduce my work, low-dimensional magnetism in new layered nitride complexes. So, the nitride complexes, due to the geometric feature of the nitride group is A03, can exhibit some different properties, and the crystal structures also can be from different dimensions. For example, the transition atom can link to each other by the nitride group and form some anions like chains, ribbons, layers, or three-dimensional structures. So in this work, I present different compounds. For example, this compound on the right part is cobalt nitrate with two water molecules, in which each cobalt atom linked to another cobalt atom by bridging ligands group to form a square layer. And such layers connected to each other by hydrogen bonds of these water molecules. So we measure the magnetic properties, and in the compound there is a metamagnetic transition and antiferromagnetic ordering at 20 Kelvin. Also, the interesting these two compounds, they have the similar crystal structure with the transition metals in these nodes. And interesting that the cobalt compound has a three-dimensional magnetic ordering and a metamagnetic transition, and the nickel compound demonstrates two-dimensional magnetism. So also this compound in its we has a Kagome layers, and these Kagome layers connected to each other also by nitride groups, and we can see the exchange in these Kagome layers and between them with different crystallographic. So it's AB plane in the crystal structure, and this is the C axis. So like this Kagome layers and like this, they're connected to each other, these Kagome layers. And the magnetic properties of them. There is a three-dimensional exchange. And so we see also phase transitions, like structural phase transition and magnetic phase transitions at lower temperature. But we can see on this slide in this temperatures, it's about 5 and 10 Kelvin. So that's all I can think about this presentation.
Thank you. There is no question. The next speaker is the same scientist, which will be talk about synthesis and characterization of lithium iron arsenide single crystal with the electron and hole substitution in the cationic sublattice, right? Here you are.
From also my address, I have sent it to email. Two emails from my address, and there are two posters, different emails. Yes. Yes, thank you. So on this slide, I present my film about the synthesis and characterization of lithium iron arsenide or single crystals with electronic and hole substitution in the cationic sublattice. The lithium iron arsenide has a crystal structure shown in this picture. There is iron arsenide layers which separate from each other by lithium cations, and it's known that it's superconductor with Tc is about 17 Kelvin. Okay. The synthesis was made by self-flux methods. So we put the initial reagents in the crucible. The crucible was put in a niobium container with ergon atmosphere, and then this container was put in a vacuum quartz ampoule and heated like this temperature profile. So we have obtained the crystals with the substitution on the iron, a partial substitution of iron atoms on cobalt, rhodium, palladium, vanadium, and ruthenium. And here we can see the magnetic measurements of these crystals. So with the increasing of substitution of iron atoms, we see the decreasing of critical temperature of superconductivity transition. But if we make a hole doping with vanadium, there is no superconductivity at all. But in only in this compound, we can see the nematic fluctuations that we can see in other doping crystals. So I think that's all about this also. Yes.
Thank you. The next speaker is Madan Sharma, right? And also there's a certificate. Yeah. Second one will be prepared in the next conference. We will give it to you. The next speaker is Madan Sharma. Is that here? Madan is online? No. Madan Sharma, Indian Institute of Technology, Delhi in India. Is that not here? I think so. We pass to next one. Dr. Mikhail Bozoverov. I am so sorry. From Moscow State University Chemical Department in Russia. Trifluoroacetane complex compound with different dimensions based on magnetic cations, structure, and expected properties, right? If you want, if you can use it.
Hello, I'm Mikhail, and I think it was very bad to look it. And then I told you about in words, and if you're interested in my theme, you can see it in the basement hall. Okay. Okay, thank you. My objects is free 3D metal consisted anions, and we do the. Can you scroll some? Yeah, what? This is the main object of my work. It is anionic structure of 3D metal. It is maybe interesting for physics because there are if the metal have antiferromagnetic origin, the frustrated system at low temperatures. And my talk about more about chemistry or physics because we only start the measurements. But it may be also interesting for someone. In the first part of our work, we try to made anionic structure when anions so far each other, and in the right column we have the oldest structure, and left column are obtained, and we obtain series of 6 compound, and the distance between anionic fragments we increase by the synthesis condition up to 13 angstrom, and then we as an exchange interaction between anionic fragments were exclude. And I want to talk that if maybe you can scroll some up for this picture. It is maybe to name this van der Waals materials, because in 2 dimensionals the chain have large of hydrophobic groups which exclude interactions between the chains. And the second part of my work, it is the right part of poster. We try to connect the anionic fragment by the number of organic bridging molecules. For example, dioxane and pyrazine, and see may they anionic triangles interact between these molecules, and then we obtained 2 cobaltum compounds, this and this one, with the target structure. And for this we now have literally 2 days ago I have text message from my supervisor that this compound is paramagnetic, and because we do not add a plot of this poster, but for nickel maybe antiferromagnetic ordering, because there are some paper in this there are. I think that's all. If someone interested, I can try answer the question later. Thank you for attention.
Thank you very much about your information. Your Mikhail Puzovar. Here you are. Thank you very much. And the next speaker is Andrei Shilov from Moscow State University, Chemical Department in Russia. He will talk about the new superconductor structure type. Here you are.
Thank you very much. My short talk today will be as an extension for Igor Morozov lecture that was this Wednesday. So in our work, we tried to get a new layered bismuthides, and we've discovered a new superconductor in barium gold 2 antimony 2 structure type. And also we found that probably, can you scroll a bit down, please? Okay. That this structure type can be described in literature somewhere wrong, we were able to refine its space group and also found a disordering in the one of the layers in the structure, which wasn't reported before us. So we obtained our crystals with a pretty standard self-flux technique, which can be found everywhere. We just used a simple aluminum crucible, which was sealed in niobium tube, and later this tube was sealed in a quartz sample to prevent it from oxidation in a muffle furnace. So we were able also to measure magnetic susceptibility, which can be found on this plot. We found that we have a superconductive phase change at about 5 degrees Kelvins. So later we tried to get a clean resistivity plot, but at the moment we performed these measurements. We had to use a conductive glue to make contacts that was attached to the crystal, and unfortunately, it reacted with our crystals. There is interesting that we, despite of this fact, we were able to identify all three phases. And interesting there is that two phases that were formed during the degradation process is superconductors too as well. So and both of them can be achieved during a simple synthesis. As example, barium bismuth superconductor can be achieved only at high pressures like 4 gigapascals, and gold 2 bismuth can be formed only during low temperature synthesis below 300 Celsius. So in the future, we wanted to measure the resistivity more carefully using indium contacts exclusively to avoid any degradation, and there will be interesting to measure more transport data like an Hall effect, and probably use some DFT calculations to because the conductive layers in this structure is bismuth gold layers, and bismuth and gold, both of them, they have a huge spin orbit coupling effects, and it will be interesting to look into interplay of these effects and superconductor properties. I think that's all.
Thank you very much. Andrei Shro. Thank you very much.
Thank you.
Yes. Yeah. The next speaker is Stefania Pizzini, CNRS Institutionnel, and in France. Is that here? Online? Nothing. So Stefania Pizzini is not here, I think. So the first session is finished. The next session about van der Waals materials. So on that session, the first, second speaker is Christos Pomorsky, Dr. Pomorsky. He will talk about, you will see because the long sentence. Erilog simulation. Erilog, is it? Yeah.
there is so perhaps one can magnify those two plots which are here. So and then next stage, there's quantization of equations of motion that can be done in two different ways. Of course, very old scheme is Bohr-Sommerfeld quantization scheme. So the system have a integer value of net angular momentum, and more kind of deeper way is by introducing two particles interacting perturbatively in Schrödinger formalism, and also it can be done in tight binding model. So could you please magnify maybe those two plots just to see, because probably visibility. So our target is to implement this simple simulation to a hardware description language in Verilog. And so one can construct the controller, hardware controller of a nanorings that can work in an effective way. So that's it. Okay. So this is, yeah, so that's it. Okay, the next one is also your yeah. So about modeling yeah, so could you make it full zoom, please? Full screen mode, okay. So the interest is basically that right now you have transition from classical games to quantum games that can be run on the quantum computers and expressed by quantum hardware. So the starting point is well-known classical Conway game of life. So there's 3 rules. If a dead cell has exactly 3 neighbors, it comes alive into the next cycle. Another rule is if a living cell has 2 or 3 neighbors, it survives in the next cycle, next time moment. And if cell has a different number of neighbors than mentioned above, it is going to vanish or be dead in next cycle. So this deterministic Conway game of life that can be expressed on 2-dimensional lattice, right? So then can we move a little bit downward so I can see there's another plot? Yeah. So can you magnify those two, please? Yeah. So then we can perturb the rules of deterministic Conway game of life by introducing the stochastic rules for transition. So transition, there were rules that were described above, are with certain probabilities. And then we can come using 2 different measures of entropy that, for example, if there are fluctuating barriers, one can witness the saturation of entropy with certain level of noise. And this is like thermodynamics law, but here the mass preservation of this is not conserved. So that's kind of characteristic for that. So this is like expression of a classical stochastic game of life. And then of course, that first thing that comes into intuition, if you have 2 different reservoirs, you can have perturbative interaction if you introduce some small holes when cells can go through this cellular automata. And then, of course, you can use the well-known methodology of statistical physics, classical statistical physics. So you can define entropy. So system maximizes entropy. And then, of course, you can define the notion of temperature by ds over the dE over ds. But then you need to define the notion of energy. And so how we are going to do it? Okay, before that, we can shift into a kind of continuous existence of life's vividity between like 0 and 1, right? So there is a kind of obvious analogy of quantum mechanics that we can somehow assign the 2-dimensional wave function that is defined on this lattice. And could you go up to this? Excuse me. Could you go up to this? Yeah, thanks. Can we magnify it a little bit? Yeah. So basically, we can describe these transitions from one state to another state by constructing artificially made Hamiltonian for the system. So the equations of motions are preserved as in quantum mechanics. And then there is some analogy to a single electron devices that can be expressed by tight binding model. This is localized energy on the left and right quantum dot and transfer the Hoping term. So basically, one can define very Hamiltonian that has some non-locality behavior. So this is so it's like annihilation of state in one place and the creation of another place, and there is this dependence of the term which depends on the neighborhood. And can we go down? Yeah. So then, could you magnify this, please? Yeah. So basically, here we also deal with anomalous features of Hamiltonian and non-harmonicity features, which can assign for dissipation, which is a good thing, because the dissipation is like non-conservation of mass or normalization of a wave function. So we can describe stars becomes alive or that dies out. So this is like expressed by an imaginary part of eigenenergy in a way. So that's this direction towards quantum game of life. There's also a continuous version of that is not yet presented here, but we are working on that. So having this notion of energy introduced by such type of Hamiltonian, we can also define temperature in our Conway game of life, and then we can broaden this concept. Thank you.
Not now. Yeah. I will give you one more paper. Thank you very much. And next speaker is Igor Morozov from Russia. Your colleague, I think. That's okay. Oh, your supervisor is not here, but you are here. Good. So this session is finished. The next session, only one speaker we will talk. Vivek Kalkani, graduate student from USA. Is that here? Not here. The next speaker in the next session, Nadim Kaiser. Am I right? Kaiser. Nedim Kaiser. 2 and 3 dimension, 3D materials based sketchable and flexible electronic in the perspective of biomedical applications. Here you are.
Hello, my name is Nadim Kaiser. Thank you for giving this opportunity. So I will talk about how we can use 2D and 3D materials for working now. Hello. Okay. So I will talk about how we can use 2D and 3D materials to get a better performing stretchable and flexible electronics in the perspective of biomedical applications. So I have a lot of checks to understand how it really affects all these things. So I will go briefly on 2-3 different perspectives. So number one, for example, we will take copper as a material, and then how this copper-based microfluidic actuator can help for our daily applications. So as an introduction, the stretchable and flexible electronics are the devices which are actually, you can stretch them and flex them or bend them, and there will be no difference or any effect on their performance, like your electronic gadgets or wearable watches or all those electronic devices. So I do study their design and mechanics to improve the performance of those devices. So let's see this figure. So in this figure, you can see there are a fair square shape. So that's called island. So that island has electronic components. So you can implode those components on those islands, and there are a few like stretchable interconnects. So using this specialized design, you can stretch your electronic device. Okay. So for this case, I use copper, and we developed a microfluidic actuator. Okay, you can go down, please. Yeah. So you can see I have used a copper-based microheater. Okay, and on this heater we spin coated polymer that is expandable. So when you turn on electrical signal, so it will expand here, and it will actually let or allow pass through a fluid. So that will like a electronic pump or electronic switch or something. So we call it microfluidic actuator. So based on copper. Another example, can you go up, please? Yeah, here. So another example is using a CNT, carbon nanotubes. So I developed this point of care real-time monitoring human muscle swelling. So in the this patch using the CNT, so it's actually piezoresistive sensor. So you can implant this sensor on your this chin part. Okay. So if there is a mumps or any infection, so you will have a physical expansion. So this patch can give you the or track the physical expansion of your muscle. Okay. And the most, I mean, the remarkable thing is we can track on phone. So your doctor can just see the swelling pattern over the time and can decide beforehand. Okay, so third example, this is, you can see here, like we tested on, you know, like dummy, and then we can see change in resistance, and it has very repeatable, you know, all the performance. And this is the function of muscle motion. So these sensors can also be used to detect the human motion for security purpose or all these things. Third one is graphene-based on-skin sensor. So this sensor also was developed to track different pressures and different functions, pressure, temperature, all those things were embedded into one single patch. Okay, so this work also, this is just accepted into ACS Nano. So that's it. Just I wanted to highlight how we can use 2D and 3D different materials to enhance the performance of stretchable or flexible electronics. Thank you very much.
I just opened. The next speaker in the next session, Sandeep Kumar, Indian Institute of Technology, Delhi in India. Is he or she here? Not here. So the first speaker in the next session about advanced in quantum materials, Dr. Krzysztof Pomorski, Krakow University of Technology, Poland. Here you are.
Hello, everybody. Yeah, so it's my pleasure to describe my last poster. So this is about description of coupled field-induced Josephson junction in curved Ginzburg-Landau equation. So the idea is as follows. So we do have a superconducting nanowire. On the top, we place ferromagnetic strip. We can place insulator in between. So quite obviously, there is modulation of superconducting order parameter coming from the existence of ferromagnetic strip. We can also use external sources of vector potential that mimics behavior of ferromagnetic strip. And in such way, there is certain difficulty in superconducting order parameter that is induced. So this is like field-induced Josephson junction. Well, here we have a cases of straight lines, but we can deform lines. So that's why it can be curvy of any shape. And also we can introduce the polarizing current that is generating vector potential that affects superconducting order parameters. So this is the case of curved field-induced Josephson junction. It can be also expressed in 3 dimensions. Well, we also have a 2-dimensional versions of that. So we can have a network of Josephson junctions. We can place ferromagnetic or non-ferromagnetic strips. So we deal with unconventional Josephson junctions. And here, what is underlined in this poster, perhaps we can magnify this part, is that we express this by this. We go around one wire. Could you please magnify it? This part. Yeah. So we because it's a little, yeah. So we have 3-dimensional Ginzburg-Landau equation, but these operators can be defined by S parameter. So effectively, 3-dimensional equation can be reduced to quasi 1-dimensional of this form, where the curvature is encoded in these functions. So can we go down, please? Go down, yeah. So we finally end up in such type of equation. So we have this F and Fs and the GS functions that encode the curvature of a system. So this term can be seen as part of dissipative term. However, we still can also think backwards using analogy to vector potential. So we can have a imaginary and really component of artificial vector potential that is introduced by curvature of cable. So anyway, having the curvature y equal ax square, we deal with such type of effective equation where alpha and beta field is dependent on x. And can we go maybe to this part? Excuse me, to this bottom part, the top, this part. Yeah. Could you please magnify? Yeah. So yeah, we can have alpha coefficient. So we take a cable that is straight. It has alpha coefficient as given here, or has two defects like normal metal in between. So we can bend it, and then let's go a little bit downward. Excuse me. Yeah, go down. Yeah. So then we obtain we use relaxation algorithm that minimize free energy functional, and for those two cases we get distribution which is in red of superconducting order parameter. So it's a general methodology to describe an inductively coupled field-induced Josephson junctions, and that's still under the progress of development. Okay, thank you.
Here you are. You're welcome. Is that last? Yes, the next speaker is Dr. Mustafa Akdoğan from Bolu Abant İzzet Baysal University, Turkey. We'll talk about price, performance, benefit of induction heating of magnesium diboride iron wire production. Dr. Mustafa Akdoğan. I think he is not
Turkish
here.
company. You are seeing the pretties and meshes on the bottom. We have applied.
It's online. Mustafa gelsene oğlum şuraya bir. Allah. Yeah, Dr. Mustafa Akdoğan, you have a 5 seconds. If you are not here, I can shift the next one.
Hello everyone, I'm Mustafa Akdoğan from Bolu Abant İzzet Baysal University. I'm going to talk about price performance benefits of induction heating on iron sheeted MgBT wire production. We are applying in-situ process on our wires. Actually, we bought our powders from Pavisium, which is Turkish company. You are seeing the pretties and meshes on the bottom. We have applied our mixture 3 hours ball milling and with a speed of 300 RPM. We have also applied drawing to our wires to reach the final diameter. At the beginning, our iron sheet outer diameter was 12 millimeter and inner diameter was 9 millimeter. You are seeing the drawing machine in our laboratory and groove rolling machine. These are the dies. Finally, we get 1 millimeter diameter of wires, and we closed each end with the mechanical press, and we have applied induction heating on these wires. Actually, we tried different temperatures, and finally we get the result from the 900 Celsius for 1 minute. And we have applied pour prop technique on our samples, gotten from the center of these induction heated wires. Here are the results of our samples. Left one is for 1.9 millimeter diameter and right one is for 1 millimeter diameter. You are seeing the resistant temperature behavior of our samples. Actually, the difference between them is the bottom broadening of the TC offset behaviors of the wires. So you are seeing broadening on the 1.9 millimeter diameters offset value, So this was expected actually, because we were thinking 1 minute may not be enough for the reaction of the MGB2. So you are seeing the differences between the diameters at the bottom. So 1 millimeter diameter transition is better than a 1.9 millimeter diameter. So as we mentioned inside the topic, if we apply heat treatment on our samples with a tube furnace, it may take 6 hours to reach this kind of behavior. But if we apply induction heating on our wires, actually it takes just only 1 minute, and power consumption nearly equal to 90 watts. So there are huge differences between them, and this will be beneficial for the industrial application. Thank you for your attention.
Thank you very much. The next speaker is Dr. Hakan Güngüneş. Yes. The next one is Çiğdem Dönmez Güngüneş. The last one is Dr. Alexey Hakhornchik. He's not here, so the game is over. Everything is finished. Thank you for all of you.